Jump right into telescoping series. So only one example, one topic. I'll keep this one shorter. There is quite a few steps. I'm going to try to connect the topics of partial sums, right, with series, right, because I didn't really connect that too much in the first video. So the idea is here, if I give you a series, right, so we'll say S for series is equal to the sum of, let's do n is equal to 2 to infinity, right? This is an infinite series, and let's do 2 over n times n plus 2. Right, so we have this infinite series, and now the idea is, right, I can't add up infinite amount of things. So what I'm going to do is I'm going to go select this arbitrary value of k things, right, s sub k. I'm going to say maybe if I can show, right, that k things will converge or diverge, then I know what's going to happen with infinite terms, right? And what's our workaround been when we're dealing with infinity, right? Whenever we deal with infinity, we kind of sidestep it and go, well, how about the limit as we go to infinity? And that's similar to what we're going to do here at the very end. We're going to say, well, what's the limit as, I wrote infinity again, didn't I? It's supposed to be k. This is a k. I'll write it one more time below. But we sidestep infinity by saying, well, let's take the limit as n goes, or in this case, yes, as n goes to infinity, right? That's the way we kind of how we'll sidestep around the infinity. Okay, but we'll get to that in a second, right? This is a telescoping series. It's not easy to recognize at first, right? Essentially, we don't even know what a telescoping is, and it really does take us an example to walk through it to understand the difference between this and, let's say, a geometric series, right? So the more series you do, the easier they become to identify. I know we don't have a lot in this homework, so it becomes a little bit hard because we don't have a giant dictionary to grab from. But let's go through this example. Okay, the first thing we're going to want to do is we want to separate this. It's not quite clear, right, what is happening as n is going to infinity here. There's an n here, there's an n plus 2, right? So what we're going to want to do is split this, right? We want to split this into two different fractions using a process known as partial fractions. I'm going to write this over here, and we're going to have to do quite a bit of side work. So we're recalling partial fractions. We should have seen this in another class, but it could have been a long time ago. And what we're going to do for partial fractions is we want to split up these denominators. Now, I don't know what's in the numerator, so I'm just going to say a over n plus b over n plus 1. And I want to try to solve for what's in the numerator. Well, first, I kind of want to reconstruct my denominator. How do I do that? Well, I need to multiply the top and bottom here by n plus 1, right? Because I'm trying to reconstruct, have a common denominator. So we'll have a times n plus 1, right? So now it's all over n times n plus 1 plus b times n. And now we can get this common denominator as such. Okay? So we've constructed the common denominator, and we also know what the numerator should be. Let's go ahead and simplify this out a little bit. We're going to get an plus bn. This is supposed to be a 2, huh? Like, wait a minute, I'm having typos all over the place. Luckily, I'm catching them. Plus bn plus 2a. This is our numerator. Why did I do that? I'm doing that everywhere. N plus 1, n plus 2, guys, sorry. N plus 2, n plus 2, n plus 2, n plus 2. Good. N times n plus 2. And so we'll simplify this. All over n times n plus 2. Okay, so the whole idea about this was we want a way where we can go solve for our a and b here, right? That's what we need to solve for. This is the form that we want up here, but we need to solve for that numerator, right, the unknown coefficients of a and b. Luckily, we have this information. So I have a numerator over here. Right, and I have a numerator over here. And I know that these two are equivalent. Right, so now it just becomes kind of a matching game. Notice on the left-hand side, this has an n. There's no n's over here on the right-hand side. So I know that a plus b is equal to 0, right? Because there's 0 n's, right? You could think of plus 0 n over here. And lastly, we know that 2a is equal to 2, right? So we actually know what a is. A is equal to 1, which means, right, b, we'll put it right here, is equal to -1, right? In order to make a plus b equals 0 must be true. Okay, so this was a lot of side work. Take a second, go through this one more time. This is what's called partial fractions. Right, I know I'm going through it quickly. I just don't want to make this example very long. And so now what we're going to do is use our coefficients and plug them in over here. So let's go ahead and rewrite. So we know that s of k is equal to, now I'll rewrite this correctly. This is a k here. N is equal to 2. And we're going to rewrite this as this, so it's 1 over n minus 1 over n plus 2. Okay, so we're going to pause, take a quick break. I'll run the matrix loading screen going through, stretch it out, we'll come back. Okay, we're back from our quick intermission. Right, now that we have it in this format, why is it called a telescoping series, right? So it takes a little bit of staring at, and again, once you do more telescoping series, obviously the pattern kind of emerges and we understand. But I mean, not to sound like a downer, but it would probably take about 50 problems of telescoping to be like, okay, that's a telescoping just by looking at it. All right, so it does take a while. But what I want us to do first is just to be able to plug in values and see what happens, right? So if I plug in 2, what happens? Well, I get 1/2 minus 1/4, right? And just keep doing this for a while, right? Just do a few terms. This is 1/3 minus 1/5. And you're like, why does he just keep writing terms? Is he planning to go to infinity? No, that's not what I'm doing. We'll see after a while. Okay, so you can already see maybe, right, what starts to happen. I'm going to do a few more down here just to really drag out the point. And we'll do one more. Plus dot dot dot. I'm going to put this one here. The last one is going to be 1 to the k minus 1 plus 1 over k plus 1. And our last one will be plus 1 over k minus 1, this is a plus, minus 1 over k plus 2. Right, that's what would happen. This would be our last term, right, if we went to k values. You're like, why did you write out so many of these terms? Well, let's see what happens. What's going on here? Well, we have a 1/4, we have a 1/4, they go away. We have a negative 1/5. We have a positive 1/5. They go away. We have a 1/6 and a negative 1/6. They go away. This went away already. And so what you're going to notice is if we kept writing this, everything would go away except for 4 terms, right? And there is a pattern, right? That's why the more we do them, the easier it is. The first term and the second term, maybe there's a pattern because this is n plus 2, so the first 2 terms stay. And also the last 2 terms stay. Everything will cancel out except for this term here and this term here. right? You can imagine the one before would cancel out this one, the one before that one would cancel out that one, right? So these last two terms here will hang out, and the first two terms will also stay there. So this simplifies, right, to just s sub k equaling 1/2 plus 1/3 minus 1 over k plus 1 minus 1 over k plus 2. Right? And you're like, well, what do we do with the k's? Well, remember what I said at the very beginning, right? I said we kind of sidestep the infinity by at the very end, we take the limit as k goes to infinity. And so now this is supposed to be infinity. And so now we get the point, right? Well, these are fine. These are just constants, or not constants, but just actual values. But these numbers over here, right? 1 over infinity is going to go to 0. 1 over infinity is going to go to 0. So we'll just end up with, which ends up being 5, 6. Right, so again, that seems to be our common thing when we have that value of infinity. How do we kind of sidestep it? Well, let's place some arbitrary value k, which for us would be our partial sums, right? This ends up being k partial sums. And then we're going to take the limit as k goes to infinity to approximate that value. So now in this case, right, the hard part kind of was the partial fractions. Once we get to this, it's about identifying that this is a telescoping series. Once we know it's a telescoping series, we know things are going to start to cancel out. And again, there is a pattern here. This is a 2. We keep the first two terms, last two terms. You could imagine if it's a 3, we keep the first 3 terms, last 3 terms. So that pattern will keep going. After that, we need to make sure we're taking the limit as k goes to infinity in order to approximate the series. Right? In this case, we get 5, 6 after everything's said and done. Right? So quick example. Again, watch this, ask questions in class. I'll see you guys later.